lecture 1 on the course of electrical circuits and network analysis. In this lecture, at first I will discuss about the signals. Okay, so the course will start about signals. Okay, so what is a signal? A signal is represented mathematically as a function of one or more independent variable that provides the information. So this is basically the signal. If a signal depends on a single variable, then it is called as one dimensional signal. And if a signal depends on two or more variables, then it will be called as multi-dimensional signal. Right? So these are two classification, basic classification, one dimensional signal and multi-dimensional signal. Okay. Now, if the system responds to one or more input quantities, then it is called the input signal, or it is said excitation. This is the new term, excitation. Excitation or input signal. If the system responds to one or more input quantities, then it is said excitation or input signal. And to produce one or more output quantities called output signal or response. Okay, this is just the theory part, nothing else. Now I will come the major classification of signal. Okay, so basically there are three major classification signals. There are three major classifications. The first one is continuous time and discrete time signal. Okay. The second one is periodic and non-periodic signal. Okay, and the third one is odd and even signal. So there are three major classifications of signal. First one is continuous time and discrete time signal. Second one is periodic signal and non-periodic signal. And the third one is odd and even signal. Right? So at first, let me start with the number one, continuous time and discrete time signal. Okay. So what is continuous time signal? The continuous time signal means the signal has a predefined finite value for each point of time. If I draw a continuous time signal, suppose this is a continuous time signal, this is the time axis, the x axis, and this is the signal xt. So this is an example of continuous time signal. That means in each and every point, if I mark this is a point, this is a point, this is a point. So these are the point on the curve. Okay. So each and every point there is a finite predefined value. So here is a point, it has a finite value in x and y axis, that means the coordinated, nothing else. The second point, it has also a finite coordinate. The third point, it has also a finite coordinate, similar like that. So each and every point, it has a finite value. So it is called the continuous time signal, right? And what is discrete time signal? Okay, before that, the continuous time signal is also called the function of real valued variable. It is also called a function of real valued variable. That means all the finite points are real. Okay, the value of the finite points are real. Okay. Second one is discrete time signal. Discrete time signal means there is some sequence of values. Okay, some sequence of values is defined for every discrete point of time. For every discrete point of time means nothing. The signal is not continuous. That means if I draw the waveform of discrete time signal, so this is the time axis, and suppose this is the origin. Okay, this is the origin. So this is the number 1, this is 2, this is 3, 4, etc. So that means the value of the 1, that means, so this is a function or signal xt. So this is denoted by x1, and this is denoted by at the point 2, at the point 2, this is denoted by x2. At the point 3, suppose the magnitude is x3. The point 4, the value is x4. Right? That means the signal is not continuous. It has every discrete points. That each and every discrete points are called samples. Okay. One more thing have to be mentioned, that is the continuous time signal is denoted by, suppose x is the signal and the continuous time signal is denoted by x first bracket of t, that means time dependent. Okay, x is a function of t, right? Whereas the discrete time signal is denoted by, suppose x t is a function of time or signal, it is denoted by x within third bracket t. Okay, the first bracket represents the continuous time signal, whereas the third bracket represents the discrete time signal. So this is an example of discrete time signal. Okay, so also the discrete time signal also may be called as a function of integer valued variable. That means in negative x-axis there may be some point. Suppose this is x minus 1. Suppose this is x minus 2. That means it is an integer valued variable. Okay, that means the range is minus infinite to plus infinite, the integer value. Okay, so this is the discrete time signal. It is also called as the function of integer valued variable, whereas the continuous time signal is called as the function of real valued variable. Okay, next topic, the number 2 is periodic signal. Periodic and non-periodic signal. Okay, so a signal is basically nothing else a function of time. Okay, so signal that is represented by ft, okay, is said to be periodic when is said to be periodic if it satisfies the condition ft equal to f of t plus minus n capital T, where n is a positive integer and capital T is the time period. Okay, that means the signal is periodic. That means the signal repeats itself after the t time period. In each and every t time period, the signal repeats itself. Okay, if it repeats, then the signal is called the periodic, where n is the positive in integer. That means if n equal to 1, that means t plus capital T. If n equal to 2, that means t plus twice t. That means second time period. 3 means third time period. That means the signal repeats itself, nothing else. Okay. So if I draw a periodic signal, the example, that means, so this is the time axis. Suppose this is the function, a signal. So this is a waveform of periodic signal. That means, look carefully. Suppose this is a 0 or origin. This time period is capital T. The second time period is 2t. Third time period is 3t, 4t, etc. That means after first capital T, the signal repeats itself and then ends in twice t. Then again it repeats itself and finishes at thrice t. That means the signal is periodic. It is similar. Each and every time period t, it repeats itself. Okay. Suppose one more example. This is the time axis. The similar thing is happened here. Suppose this is t by 2. This is t. Similarly, this is also 3t by 2. This is twice t. That means the signal repeats itself. So it is called the periodic signal. This is the origin. Okay. Then what will be the non-periodic signal? Non-periodic signal means simply the signal who violates this condition. This is the main condition for a signal to be periodic. The signal which violates this condition, that means ft equal to f of t plus minus n capital T. So this is called the non-periodic signal. Okay. Non-periodic signal, the example of non-periodic signal, the example of non-periodic signal are, suppose, exponential signal, ramp signal. I will go on the details of exponential signal, ramp signal later. Okay. So these are the common example of non-periodic signal, that is exponential signal or ramp signal, and the example of periodic signal is square signal, triangle signal. Okay. So this is the periodic and non-periodic signal concept, right? Third one. Third one is odd signal and even signal. Odd and even signal. Okay. So what is odd signal at first? A signal, which I have already told, is a function of time basically. A signal ft is said to be odd if ft equal to minus of f minus t. This is the main condition for a signal to be odd. That means ft is equal to minus of f minus t. The example of odd signal is sinusoidal signal. Very common example, right? So this is the time axis, basically omega t. So this is the signal ft. So this is a sinusoidal signal. Ft is equal to sin omega t. So this is ft equal to sin omega t. If I put t is equal to minus t, that means f of minus t. So it will be minus sin omega t, because sin of minus t is equal to minus sin t. This is a very common knowledge from our class 11 or 12 syllabus. Sin of minus t is equal to minus sin t. So that means f of minus t is equal to minus sin omega t, right? So this is the example of odd signal, right? And whenever the signal is even, that means the criteria. So this is the criteria for odd signal, and the criteria for even signal, that is ft is equal to f of minus t. That means this is the criteria for even signal. Look, minus sin omega t means minus ft, minus f minus t, minus f minus t. Sin omega t is equal to ft, that means minus sin omega t is equal to minus f minus t, right? Even signal, very common example of even signal is co-sinusoidal signal, which is basically 90 degree lead from the sinusoidal signal. If I draw the graph, that means this is the example of co-sinusoidal signal. This is the omega t and this is your ft. This is an example. This is the sinusoidal and this is co-sinusoidal, which is 90 degree lead from the sinusoidal signal, nothing else. Suppose ft is equal to cos of omega t, right? This is our from. If we put t is equal to minus t, then what happened? Cos of minus omega t, that is equal to cos omega t. It is already known to us from our basic knowledge. Cos of minus t, that is equal to cos t. That means we have got f of minus t, that is equal to we have got ft is equal to f of minus t. So this is an example of even signal, right? At next, each and every signal can be decomposed into its odd and even components. This is quote unquote, this is a habitual truth. Okay, each and every signal can be decomposed into its odd and even components, right? So suppose ft is a signal, and what is the rule? ft is equal to f odd t plus f even t. F suffix o, that means f odd component, plus f suffix e, that means f even component. This is a habitual truth. That means every signal can be decomposed into its odd and even components, right? Look, if we put t is equal to minus t, then suppose this is your number 1 equation. Okay, if we put t is equal to minus t, then what will happen? Then f0 minus t, f odd minus t plus fe minus t, right? Okay, So f odd of minus t, that is equal to, we have already got minus f of odd minus t in your previous session, that is f for odd signal, ft is equal to minus f of minus t. Okay, minus f of minus t, that means minus f of minus t plus f even minus t, that is equal to f even t. That means f of minus t is equal to this. Okay, that is already that has been already got. That is for even signal, f t is equal to f of minus t, right? Simply just we put the value. So this is your number 2 equation. Okay, this is your number 2 equation. So sorry, there is a small mistake. It will be minus f of t. Okay, f or minus t will be minus of f of t. Okay, so if we add and subtract in between number 1 and number 2 equation, if we first we add the two equation 1 and 2, second we subtract the equation 2 from the equation number 1, then what will happen? Suppose first adding, first case equation 1 plus equation 2, equation 1 plus equation 2, then what will happen? Look, f of t and minus f of t will be cancelled out. That means f of t plus f of minus t, that is equal to twice f of even t. So finally we got f of even t, that is equal to half of ft plus f of minus t. Clear? So this is very important. When we add these two equations, number 1 and number 2. Secondly, if we subtract equation 1 minus equation 2, if we subtract, then what will happen? Look, f even t, that means this term, f even t and f even t will be cancelled out, where f of t minus of minus f of t, that means plus twice f of t. Okay, that means twice f of t will be f of t minus f of minus t. So f of odd t equal to 1 by 2 ft minus f of minus t. So these two equations are very important. Okay, this is basically the proof how we can say that each and every equation can be decomposed in its odd and even components. This is the proof, right? Clear? Okay. Next, other than that, so we have already discussed rather the three major categories, that is continuous signal and discrete type signal. The second one is periodic signal and non-periodic signal, and the third one is odd signal and even signal. And from that, I have already discussed that the each and every signal can be decomposed in its odd and even components. Okay. Apart from that, there are two categories. There are, from the three major categories. Apart from that, there are also two other categories. First, the first thing is some special signal. Some special signal. Special signal means under this category, there first one is sinusoidal signal, the second one is cosinusoidal signal, and the third one is exponential signal. Okay, very simple. Sinusoidal signal. So this is the graph of sinusoidal signal. This is the omega t. Suppose this is the signal if suppose this is signal Vt. Okay, supply voltage for an example. So what will be the equation? Equation will be Vt is equal to Vm sin omega t, right? Where V is a function of time. Vm means the distance, that is the peak value from the origin and its peak. So this is called Vm. Okay. Vm is the amplitude. Vm is amplitude. Okay. Where omega t is the argument, and omega is the angular natural frequency. The unit of omega is radian per second. Okay, and what is the value of omega? Omega equal to 2 pi f, where f is the supply frequency. So it may be written as 2 pi by capital T, because the supply frequency is inversely proportional with the time period, where capital T is the time period. Okay, nothing else. Then so this is called the sinusoidal signal. Sinusoidal signal. Okay. Next is cosinusoidal signal. Similar thing. So this is the graph omega t, and this is your signal, suppose Vt. So cosinusoidal signal means, so this is the cosinusoidal signal, which is basically lead 90 degree from the sinusoidal signal. So similar thing. So Vt is equal to Vm cos omega t, where Vm is the amplitude and omega t is the argument, where omega is the angular natural frequency. Similar case, nothing else. Okay. And then after that, exponential signal. Third one is exponential signal. Exponential signal, suppose ft is a exponential signal. For our example, ft, it is equal to 0 whenever t less than 0. The criteria of exponential signal. Okay, and ft is equal to, the equation will be k e to the power minus at when t greater than equal to 0, where k and a are some real constant magnitude, nothing else. Okay, so if I draw the graph of exponential signal, that means ft is equal to k e to the power minus at. That means, suppose this is the point k, Gaussian magnitude, the graph will like this, consistently decaying graph. Okay, and from k is a constant magnitude. So this is the equation, ft, that is equal to k e to the power minus at. Okay, And one more thing that should be mentioned here, that is A. Okay, the inverse of A, that means the reciprocal of A, is called time constant. I am not going to the details in this lecture about the time constant because it will be discussed on the subsequent lecture. Okay, so that simply tau is equal to, tau means the time constant, it is represented by the symbol tau, that is equal to 1 by A. Okay, A is of some constant and the inverse of A is called time constant. Clear? Next, apart from three major categories, continuous, discrete, odd, even, periodic, non-periodic, there are two other categories. First one is a special signal. Under this category, there is a sinusoidal signal, cosinusoidal signal, and exponential signal. And the second category is called singularity signal. Singularity signal, very important for in this course, circuit theory. Okay, singularity signal means step signal, ramp signal, and impulse signal. These three signals are together called singularity signal. The first one is step signal, second one is ramp signal, and the third one is impulse signal. Okay, so at first, what is the step signal? I will go for step signal. Look very carefully. If a signal ft, suppose ft is a step signal, ft is equal to ut, that is equal to 1 when t greater than 0 and equal to 0 for t less than 0. Okay, that means this is a unit step signal. ft is equal to ut, unit step, that is equal to 1. 1 is the constant dc magnitude. Okay, that means that if I draw the graph of unit step signal, that means this is the origin, time axis. Suppose this is the point 1, the graph will be parallel to the x-axis, constant dc value, unit step signal, nothing else. And at t greater than 0, the value of the step signal is 1, and t less than 0, the value of step signal will be 0. And it is undefined, the value of step signal is undefined at t equal to 0. Okay. Next, suppose here is a step signal with constant magnitude k, that means ft is equal to constant magnitude k into ud, that is equal to k for t greater than 0 and it is equal to 0 for t less than 0, and similarly undefined at t equal to 0. So the signal, if I draw the signal, this is the t, this is the signal ft. Suppose this magnitude is k. Okay, so this is the step signal with constant magnitude. ft is equal to k, nothing else, right? Then if there is some phase shift or some delay, that means the signal does not start from the zero, from the origin. There is some phase shift by capital T. Okay, that means ft is equal to, suppose I will come to the point on unit step signal with the phase shift by capital T, that is u t. This is a unit step signal, but the signal will start from delayed from the origin by capital T second, that means t minus capital T. Why minus capital T? ft equal to ut means the signal is unit step and will start from the origin, but there is a phase shift, the signal will start from t seconds later from the origin, that is there is a delay from the origin, there is a delay, the signal will start after 3 seconds later. So ut unit step minus capital T, capital T seconds later. Okay, so this is called the unit step signal with a shift, phase shift or delayed signal. So that is equal to 1 for T greater than 0. No, T greater than capital T, because the signal does not start from the 0, it will start from the capital T seconds. There is a delay. So before capital T, the signal, the value of signal is 0 before capital T, because the signal will start from the capital T seconds. Before that, the value of signal is 0. From the capital T, the signal will start, and the value of the signal is 1, because this is a unit step signal. Unit step signal, that means the constant 1 magnitude, and start from the T seconds later. So if I draw the graph, the signal, suppose this is the T, okay, time period, time axis, and this is a function. That means this is the origin, and this point, suppose this point is capital T, that means delayed from the origin. The signal constant magnitude, suppose this point is 1 DC magnitude, so the signal will start from this capital T and then it will like this, maintaining the constant 1 magnitude. Okay, so this is the unit step signal by phase shift or delayed capital T seconds. Okay, clear? Next, according to this phase shift, there is another some function that is called the gate function. That is called the gate function. Suppose GT is the gate function or gate signal. It is with constant magnitude k. Suppose the signal have the constant magnitude k, and it is represented as k u t minus a, minus k u t minus b. That means, look, u t minus a means there is a unit step signal with a phase shift by small a seconds from the origin, and ut minus b means unit step signals with a phase shift small b from the origin, nothing else, and k means constant magnitude. But there is a difference of two signals. It's called the gate signal. So if I draw the graph, suppose this is the time axis and this is your function, this is a function gt, I have written here gt. That means this is the point small a, that is delayed from the origin, and this is the point small b, that is also delayed from the origin. That means the distance from a to 0, so from origin to a is small a, and the distance from origin to small b is small b. Okay, that means the signal with constant magnitude, suppose this value is k, constant magnitude. First of all, the signal starts from the small a, that is a second later from the origin with constant magnitude. So the signal will start from small a and then it will continue maintaining the constant magnitude k, Another signal with constant magnitude k will start from b seconds later from the origin. That means here is the point b. So also this signal will start from the point b and it will follow the constant magnitude k. Okay. Now this is the two signal. The red one is k u t minus a, and the blue one is k u t minus b. Okay, so now we have to find the difference, k u t minus a minus k u t minus c. That means this shaded region will be your gate function. That difference between k u t minus a minus k u t minus b. So if I redraw the graph, the fresh graph will be like this. The fresh graph will be like this. This is A point, this is B point. So this is the time axis, this is your signal GT. So this portion is called gate function. That is basically the difference between step signal with constant magnitude by a phase shift A and B. Okay, so this is the simpler concept of gate function. Okay, next, the next thing is ramp signal. So what is ramp signal? Ramp signal is basically the integration of the unit step signal or step signal. Basically the integration of constant DC value. Look, suppose a unit step signal is ft is equal to ut is equal to 1. If I integrate the unit step signal, then what we will get? Ut is 1 into dt, that means equal to t. That is equal to t. So this t is called the ramp signal. It is represented by small r as a function of t. That means the equation of ramp signal is ft is equal to r of t, that is equal to t for t greater than equal to 0, and the value of ramp signal is 0 for t less than 0. Okay, so ramp signal is basically a very important point. Ramp is the integration. Okay, is a very important point for MCQ question. Integration of step signal, nothing else. If we integrate a unit step signal, we find the ramp signal. So what will be the graph? What will be the graph? If I draw the graph, from the origin, the signal will be like that. So this is the signal, ramp signal. This is the time period, and the slope of the signal will be 1 because it is the unit ramp signal. Slope means the tan theta. That means this is 1. This is also 1. This is the 90-degree angle. This is the right angle triangle. What is tan theta? Perpendicular by base. The slope of the ramp signal, unit ramp signal is 1. So this is the unit ramp signal. If I draw the ramp signal with constant magnitude k, that means ft is equal to k of rt, constant magnitude, that is equal to kt. Okay, constant magnitude, that is equal to kt for t greater than equal to capital T, and if t equal to 0 for t less than equal to capital T. Okay, t less than equal to capital T. So this is the ramp signal with a constant slope k. Sorry, kt, there is a mistake, t greater than equal to 0. Sorry, and hence t less than equal to 0. Okay, this is the ramp signal of any constant slope k. So what will be the graph? If I draw the graph will be this is the ramp signal. So this is your k of rt. This is time axis. That means this perpendicular is k and base is 1. This is the ramp signal with constant slope k. Okay. Then similar thing, the shifted unit ramp signal, shifted unit ramp signal, that is equal to ft is equal to small r t minus capital T. That means similar thing, capital T seconds delayed from the origin. So it is true for t greater than equal to capital T. In this case, the condition is valid, t greater than equal to capital T, and ft is equal to 0 for t less than capital T. Before capital T, the value of the signal is 0 because the signal will start from the capital T seconds. Okay. If we draw the graph will be, suppose this is the capital T point delayed from the origin, this is the time axis, and this is your unit ramp signal R T minus capital T with phase shift T. So the signal start from the capital T. It will looks like. So this is your slope 1 and 1 unit ramp signal with T shifted, capital T shifted. Okay, shifted unit ramp signal. Clear? Next topic, the last topic is impulse signal. Impulse signal. Impulse signal is also known as Dirac delta function. It is denoted by delta t. Impulse signal is denoted by delta t. T is a function of that means a function of time. Okay. The statement of impulse signal is the signal is 0 everywhere except the instant t equal to 0. That means the value of the signal is 0 in everywhere except that t equal to 0. Basically, it is a very sharp pulse of infinitely small width. Okay, the width of the signal is infinitely small, but very sharp pulse and very large magnitude. That so think twice. It is a very sharp pulse with long magnitude and infinitely small width. That means the area under the impulse curve is always maintained at unity because it is sharp, very large magnitude, and width is infinitely small. It's just pulse signal, nothing else. So if I put the graph before that, consider gate function. Suppose this is the time axis, this is the gate function. We have already discussed. This is a gate function. Okay, suppose this is 0, this is A, this is A by 2, this is A by 3. Similarly, this thing is 1 by A, this point is 2 by A, and this point is 3 by A. Okay, and this is the function of time. Okay, so this is a gate function. We have already discussed about it. If the function is compressed along the x-axis, and stressed along the y-axis. Look, the function is compressed along the x-axis and it is stressed along the y-axis. That means compressed along x-axis means A tends to 0, compressed along the x-axis, and it is stressed along the y-axis means 1 by A tends to infinite. So in previous I told that it is a very sharp pulse with long magnitude and infinitely small width. That means then the signal will convert to this. This is the delta t impulse signal, and this is suppose infinite. The magnitude is large, infinite magnitude, and infinitely small width. this is the 0, this is the time axis. That means the area under the curve. What is the curve? The curve is the short pulse. This is the short pulse. This is your impulse signal. Short pulse. That means the value of delta t is equal to 0 for t not equal to 0. That means the value of impulse signal is 0 everywhere except the instant t equal to 0, because at t equal to 0 the value of impulse signal is infinity. The magnitude is infinity at t equal to 0, and t equal to 0.1 or 0.001 the value of impulse signal is 0. At t equal to 0 instant only the value of impulse is infinity. So the area, that means area is in integration minus infinity to plus infinity delta t dt, that is equal to 1, because I have already mentioned the area of the impulse curve is unity. So this is the concept of impulse signal. With this I am ending the today's lecture about the signals. Okay, thank you.